Welcome to Common Emitter Amplifier with Decoupling Resistor. Okay, so this lecture is going to focus on Z in, Z out, AV, AI, and AP, the gains. And so this is a common emitter amplifier using universal biasing with the decoupling resistor. The biasing is done in a prior video, so you can go look for that video and do all the DC stuff. And then we're going to do right now is we're going to focus on see if we can figure out what Zn is. So here's my eyeball. Zn is the impedance that the generator sees. In the lab that we do, we've got a capacitor right here. So that essentially puts an AC ground right there. But in this homework problem, we don't have that. So we're going to have to figure out what Zn is using the decoupling resistor R1. So I'd like to start as far away as possible, and we can see that we're talking AC when we talk about Z, so these coupling caps are doing their jobs. So they're acting like shorts. So if we start as far away as we can, we've got RL in parallel with R4. Oh, sorry, that's actually in series. We've got, because we're trying to get to this point right here. So we've got RL plus R4. That gets us to right here. In this corner now we can see that we're in parallel. That is in parallel with R1. Which is in series now with R2. That gets us to right here, in between there. So we've got an R prime E right here we need to put in. And we need to bring those two R5 and R prime E across the beta barrier. So all of that is going to be in parallel with RE5 or R5 plus R prime E. Brought across the beta barrier going from a high current side to a low current side. So we're going to multiply by beta plus 1. Now that gets that resistance to right here. And we can now see that though that's going to be in parallel, also in parallel with R3. And that is the impedance that the generator sees. So let's walk back through that. So you can see you've got the RL, if we start far away as we can, we've got RL coming this way, plus R4. Then we've got, now we're at this node, in parallel with R1. In series with R2, that gets us to right here. And now that is in parallel with this branch brought across and with R3. That's our total Zn. Okay, now let's work on Z out. Let's go to maybe lighter color. Z out is the impedance that the load sees. So again, these coupling caps are doing their jobs. We don't have the bypass cap up here. So we're going to have to factor in all that impedance. So we're going to start as far away as we can. We've got Z out equal to, we're going to start here at R gen. And our gen is going to be, get right here, it's going to be in parallel with R3 and in parallel with this impedance brought across the beta barrier, which is R5 plus R prime E, those both times beta plus 1. That gets me to right here. Now that is going to be in series with all of that, is in series with R2. That gets me to right here. And we're trying to get to the load. So you can see that R1, all of that now, is in parallel with R1. Now all of that now is in series with R4. And that is my total Z out. Okay, let's see if we can figure out AV. Now, this circuit does not have a decoupling cap, right, which would have been right here. And in our lab, we've got that cap right there. Now, because that's not there, right, we're going to need to consider all of the resistances. So for our V out, we're going to have IC times some resistance. Let me clear this. We'll back this up just a little bit. So AV is V out over VN. So I'm going to define V out and VN, and then you can put those back into the formula after. So V out, when we're looking at V out, we're looking at using IC, the collector current here, and we're looking for the AC resistance that's hanging off of that collector. So because there's no decoupling cap sitting at the bottom of R1, we're going to have to go all the way back, and this cap here is doing its job. So we've got our gen, in parallel with R3, in parallel with R5 plus R prime E brought across the beta barrier, that entire quantity. Get that kind of clear. So if you look at that right there, that gets us to this node right here. If you look at that, all of that right here, so look at this equation right here, from here to here. You've got our gen here in parallel with all that stuff. So R3 generally is usually pretty big compared to 50 ohms. You've got the R5 and R prime E brought across the beta barrier. That's going to be quite a bit larger. So you've basically got our gen at this point right here. But just to keep it all, to show you that the math really does work, we're keeping everything in parallel. We're doing exactly what's there. And so now I'm here at this node. Now I'm in series. I'm going this way. I'm trying to get back to the collector. So that's going to be added to R2. Which generally is a big resistor also. I think in our example, 27K. So Rgen plus 27K is basically 27K. Now all of that is, now we're here, so all of that is now in parallel with R1. Which 27K in parallel with R1 is basically R1. Now all of that gets us to right here. All of that is going to be in series with R4, so we're going to add R4. So it's basically, if you look at the math just and try to approximate, you've got R1 plus R4. But you can't really say that without that decoupling capacitor there. But mathematically, that's what it's going to end up being pretty darn close to. Now all of that now is in parallel with RL, and that's going to give us our resistance. For our V out. Now our V in, we're trying to find we're going to try to use IB. So we're trying to find an equivalent resistance that's sitting right here. So we're going to add R5 to R'(E) and bring that across the beta barrier and multiply that by IB. Now mathematically, if we look at this, IB times beta plus 1, we can see that that would be equal to IE. So we can now convert that to alpha because it's V out over V in. So if we kind of divide that right there, we can now say AV is equal to alpha IC over IE, which it converts in terms of beta to beta over beta plus 1. There's alpha. And then now multiply that by the R5 plus R'(E). And then the numerator, that's the denominator. The numerator is going to be the Rgen parallel with R3 and parallel with R5 plus R'(E) times beta plus 1. All of that plus the R2 in parallel with R1. Get some of this out of my way. It's in parallel with R1. And then plus the R4, and all of that is in parallel with RL. So that's your numerator. So basically your numerator is this V out formula. Here. I erased some of this stuff on accident. Okay, so that V out right there minus the IC, because we converted the IC to beta over beta plus 1. We converted that IC there. Okay, so there's your AV, which basically you can eliminate a lot of this stuff just by saying, well, 50 ohms in parallel with that is 50. That's 27K. R2 is 27K in parallel with a 1. What's R1? R1 is about 1K, so that's going to be 1K. Now that's in series with R4, so 1K plus R4 is 3.2K in parallel with the RL of 1.768K, and then simplify it right down. But if you want to write it all the way out, there's the math to write it all the way out. All right, so AI, the current gain, I out over I in. Now this is the same as all of our current gains. So we can simplify that, or we can go right to it. So our AI, oops, get this pencil working. AI is equal to AV times Zn over RL. And we've derived that several times in previous videos. AP is AV times AI.